Hi everyone. When AI writes code or answers complex questions, is it truly reasoning or just predicting the next word? What's really happening inside these models when they appear to think through a problem? In this video, we'll do a deep dive into the inner workings of AI reasoning. Keep watching to learn more. This video has 3 parts: transformers and their limitations, breadth and meta-learning, and depth with chain of thought. Part 1. Transformers and their limitations. You've probably heard that modern-day large language models, or LLMs, come from something called transformers. This is based on a 2017 Google paper called "Attention is All You Need." Transformers are amazingly powerful and general. Before LLMs, machine learning experts would create special-purpose models in every domain, for speech generation, image recognition, robotics, etc. Now, most of those techniques have been supplanted by transformers. You basically convert everything into language, even pixels, and then leverage the power of reasoning that LLMs have achieved. But when I say reasoning, do I mean it in the same way as I would when I say a human is reasoning? Well, Geoffrey Hinton, the eldest of the 3 godfathers of AI, believes that what is happening in LLMs is very similar to what is happening in our brains. When asked, "You believe these systems have experiences of their own and can make decisions based on those experiences?" He said, "In the same sense as people do, yes." So you can make up your own mind about this, but Geoffrey Hinton has been thinking about it for a long time. But how does this actually work? What is happening under the hood inside LLMs, inside transformers? I'm going to do a brief intro to transformers. They basically take a string of input tokens and they produce another string of output tokens. They transform the input sequence into the output sequence. They were originally developed to translate one human language into another. And that's how Google speech recognition works today. But the transformation can be far more complex and even involve reasoning with today's models. In particular, you can run a transformer autoregressively. That means that its output is fed back into its input in a loop. So this is the first important thing to understand about LLMs. The input is a big sequence of words that contains everything from the system prompt to the user instructions to case-specific data. Then, given that input, the transformer predicts one single token, the next word essentially, and that is added to the end of the input. And then you run the whole thing through the transformer again, the same transformer. And when it has the original text plus one word, it then predicts the next word, which is like the second word of the model's output. And then that gets added back to the input, and so on and so forth. This goes on until the model predicts a token, which is a special token, end of sequence. And then it stops. This has some interesting implications because all of the instructions are here, all of the context is here, all in the same blob essentially. Even past model answers are there. So if you have a back and forth conversation with ChatGPT, then the previous answers that the model has given are going to be in that transcript somewhere, which means that you can fake previous answers just to see what happens, because the model has no memory beyond what is given to it in the input, so it can't tell that, oh, I didn't actually say that in the past. I will say as well that there are some people that are very skeptical about LLMs. They think it's just next word prediction or just autocomplete or those types of things. But I'll take another argument here from Geoffrey Hinton, who pointed out that if you are at the first word in the response, then you need to understand the question in order to actually start generating an answer. Yes, if you're halfway through the answer, then you could make a stronger argument that it looks a little bit like autocomplete. But when you're at that first token, the model has to really do heavy lifting to figure out what to say next. Now, the point of this part was supposed to be to talk about the limitations of transformers. So let's get to that. There are 2 main types of limitations, but to get into them in detail, we first need to talk a bit about neural networks in general. Try to visualize a neural network. Basically, there are a bunch of digital neurons connected together. The neurons are arranged in layers, like this, stacked on top of each other. Each neuron has connections to other neurons, but mostly only to the next layer, or to layers that are further ahead. Sometimes there are what are called skip connections, which will go not to the next layer, but to the next layer, so to speak. The overall system is called a feed-forward neural network. The name is pretty self-explanatory because information can only go forwards through the network. It can't go backwards. Data moves forward layer by layer through the connections between neurons, forwards in time and not backwards in time. Just a side note that modern neural networks also have self-attention edges, where data can essentially flow sideways within one layer, but it's still flowing forwards in time. Let's talk about width and depth. A neural network has a defined size. It might be really big. For example, current frontier models might have 1 trillion parameters or more. For what it's worth, the number of neurons will be less than the total number of parameters because the number of parameters grows much faster. It's roughly width squared times depth, or width times depth. But anyway, each layer has a fixed number of neurons, and we can call that the width of the neural network. And then there are a certain number of layers stacked on top of one another, and we can call that the depth of the neural network. So the limitations are that because the neural network is finite and it has a fixed width and a fixed depth, well, either of those could be too small to solve the problem at hand. First, let's talk about the width or breadth, the width limitations that could arise. Well, the width of the neural network roughly corresponds to how many things it can think about at once, or maybe how many hypotheses or trains of thought that it can pursue at a single time. How much is in its working memory? So making a neural network that is wider will cause it to consider more hypotheses and have more reasoning pathways. But there is a quirk in how transformers work. If there are k tokens in input, then it only produces k parallel computations. It's kind of like each token of input is a variable that the LLM can manipulate. So this means that in the beginning, when dealing with a shorter prompt, for example, an LLM could be limited in terms of the breadth of its computation. Pause tokens address this, and we'll talk about that in part 2 of this video. On the flip side, you could be limited in terms of the depth of the neural network. The depth effectively corresponds to how long is the LLM thinking about a topic. So because the depth is a finite size, that means that the LLM can only think about something for a finite amount of time before it's forced to output another word, the next word, which means that if a problem is really complicated and you have to do a bunch of steps one after another, the LLM could well not be able to actually do that in one forward pass. And even for frontier models, there actually aren't a lot of layers. For example, there are 96 layers for GPT-3, 61 for Deepseek, and 126 for the largest Llama 3 model. So this leads to shallow reasoning, right? Because the LLM can't think in depth about a topic before starting to produce an answer. There is a technique, however, called chain of thought, which addresses this, and we'll talk about that in part 3. But now for part 2, breadth and meta-learning. As I mentioned earlier, the breadth or the width of a neural network could be a limiting factor in terms of the computations that you can perform. And one way to address this is through a technique called pause tokens. The idea is to create a pause token, a word essentially, which has no meaning. It just exists to use up space in the input sequence. By making the input longer with pause tokens, you give the model more variables, essentially, more space in order to perform the computations it needs to do. When you do this, the computational depth is unaffected. And remember that the neural network has a finite width. So what's going on here? We're essentially adding tokens, and it seems like we're expanding the width indefinitely. The transformer has inside it this attention mechanism that lets it pay attention to the variables that it cares most about in the input. So you're just giving it space to think. It can then spend its attention wherever it wants on that input, and it still gets a finite amount of time because the depth is unchanged. Okay, but how do you do this? Well, all of the different stages of model training have to be modified. You have to go back and do pre-training and insert pause tokens randomly throughout the corpus so that the model learns that the pause token means do nothing. You have to fine-tune as well on data including pause tokens. And finally, at inference time is when you can actually use the pause tokens and you append them to the end of the input. Again, because if there are k tokens in the input, then it can really only have k variables or k spaces for thinking when it's doing the computation, but if you increase that, it has more space. And then at the end, all of these parallel computations will be kind of combined together and the best one will be selected. And this pause token method can increase the performance of a model by up to 18%, like the accuracy in terms of certain benchmarks, which is really significant. The only cost you pay is that there's a lot more memory consumed because you're actually including more tokens, and a lot more compute consumed, like GPU computations as well, because the amount of compute needed goes up as you have more tokens. And there's another paper similar to the pause tokens paper called Let's Think Dot by Dot, which is a funny play on the original prompt that got models to think carefully by saying, let's think step by step. Anyway, in this case, a dot, or 3 dots like an ellipsis, represents the filler token here. This is similar to the pause tokens that we were talking about previously. To go into this idea, I would like to first talk about internal algorithms. Neural networks are very much black boxes to us. We can't really see what's going on inside them. But as we feed a neural network more and more data, it figures out a lot of shortcuts and abstractions. It actually develops internal algorithms that we don't really understand for searching data and solving problems. These algorithms develop naturally. We didn't put them there. And when it does this, the neural network isn't just memorizing information, it's learning how to learn. When you give this neural network a new piece of data, it will apply its internal algorithms to figure out how to classify this data and understand it, and it should be able to understand it more quickly with fewer repetitions of similar input data. This behavior, to be able to pick up the skill of learning itself, is what we call meta-learning. As machine learning practitioners, we define how the model's learning will work, kind of like defining how evolution would occur. Then you put data into the system, and naturally, interesting creatures evolve. In particular, one algorithm, called gradient descent, is very important for deep learning. It tells you how to update model weights after seeing a positive or negative example during training, for instance. The interesting part is that even algorithms as complex as gradient descent can actually develop within a neural network as an internal algorithm. It's like a nested gradient descent, really, because when we defined evolution, we defined it by using gradient descent on the outer scope, so to speak. And then that system itself figured out how to do gradient descent within the model itself. This means that neural networks could try to solve the types of problems that we normally train neural networks to do, except normally we need lots of training data, and it could try to solve it with no training data. And that's called in-context learning. Neural networks can also develop other types of internal algorithms like heuristic search and mesa optimizers. Anyway, enough about that, and back to the thinking dot by dot paper. In this work, the authors ask the model to output filler tokens, which are basically dots, before outputting an answer. It's basically like a chain of thought full of empty tokens, if you're familiar with that concept. You might wonder how this could be useful to the model. After all, the same model keeps getting invoked for each forward pass, and it's not writing down much information to indicate what it thought about previously, right? It's outputting just a dot token, like a filler token, and that gets added to the end of the input. But unless you're counting from 1 to 100 or something, there's not much you can do there, right? Yet this paper showed that there are certain classes of problems that the model couldn't normally solve, but by adding a lot of filler tokens, it's able to. So what's happening here? What's happening is an internal algorithm called a mesa optimizer. A mesa optimizer is an internal algorithm that optimizes towards some specific internal goal. Remember that when we train a neural network with gradient descent, we give it an overall goal to achieve. But it's possible that during this overall optimization, the network itself creates its own internal goals and optimizes to reach them before presumably trying to solve the overall goal. In this case, the neural network has extra filler tokens in which it can put some internal state. Effectively, the width of the neural network has artificially increased, just as for pause tokens. So the neural network has more space to do its own computations. The difference here is that the model gets to choose how many filler tokens it outputs. Those extra slots can be filled with the data for whatever internal algorithm that the model has developed. And again, the mesa optimizer that is solving for, oh, you have more data space, seems to be better than the original model at solving this problem. In fact, certain problems with 2 or more logical qualifiers are difficult for the original model to solve, and they become nearly 100% solvable with the extra computing space. However, it's worth noting that these very interesting results only occur after the authors modified all 3 stages of model training, which are, again, pre-training, fine-tuning, and the prompt. The model has to learn how to use these filler token slots. Otherwise, filler tokens are really out of distribution, meaning that the model has never seen them before in its training data, so it doesn't know what to do with them. Part 3, depth with chain of thought. By far the biggest limitation with neural networks is not the breadth of their computation, but the depth. Width corresponds to having thoughts in parallel, but depth corresponds to how long you can think about a particular problem. And in order to increase the depth of a neural network, we have to use multiple forward passes. However, the way that transformers work, no state is really passed from one forward pass to the next. And the model is supposed to output a token, the next word in the answer. This is where chain of thought comes in. It's basically when you ask the model to break down a problem into smaller steps and then do the steps one after another. Chain of thought was originally a prompting technique where you said something like, please think step by step, or please break the problem down into smaller pieces and solve them one by one, something like that. But these days, chain of thought typically refers to a particular type of fine-tuning where you ask the model to output thought tokens. So you basically tell the model, okay, the first couple of tokens that you output are not going to be part of the real answer. They're just your scratch pad. It's where you can put down your thoughts, your chain of thought, which is hopefully going to be constructed, again, as breaking down the problem into small pieces and essentially writing it down. In theory, this works for the same reason that it's much easier for a human to do long division on paper. When you have this scratch pad, this extra memory, you don't have to put as much in your head all at once. Mechanistically, the way this works is that the model first outputs a think token, then as many intermediate thoughts as it likes, followed by an end think token. And then finally, it can output the real answer. This works surprisingly well, and you don't even have to modify the really expensive pre-training phase. You just have to run fine-tuning so that it understands the think tokens and the structure that you're expecting for a chain of thought. For Deepseek, for example, they pre-trained a model called Deepseek v3 on tons of English and Chinese text. Then they created a supervised fine-tuning data set to fine-tune the model for chains of thought, and they had to actually use synthetic data generation to have one model generate even more chains of thought for the other model to learn from, because they just need a lot of data. But at the end of it, they had come up with Deepseek R1, which is their reasoning model that uses chains of thought. In some ways, we are doing ourselves a disservice by calling this a chain of thought, however. Let me explain. A chain of thought is supposed to be an explanation. It kind of makes sense if you read it as a human, though it tends to wander a lot. It's in understandable human language because that's what the model has learned the most about. However, this does not necessarily mean that the chain of thought is actually what the model is thinking. It's very easy to make this mistake, and according to a recent study, about 25% of the interpretability papers that they looked at were making this error. Think for a minute back to how a chain of thought is generated. In the forward pass, the model can be performing a lot of internal computations. It might have some internal algorithms and so on. It can kind of be doing one parallel computation for each input token, assuming that it has enough attention to go around and perform all those computations. And ultimately, it has to generate a single output token. The model has also learned from the fine-tuning that the chain of thought is supposed to be understandable English. So sometimes the next token will be highly determined by the context, just because of English grammar. But when it's starting a new sentence or phrase, the model can really point itself in a different direction. And yet, the words produced in the chain of thought are trying to make a certain sort of sense and trying to guide the model away from dead ends that it has looked at previously. But it does not correspond to how the model is actually thinking. The model's internal thinking is matrix multiplications on really large vectors. It has nothing to do with those logical sounding English sentences in the chain of thought. It's true that the model's only way to avoid thinking exactly the same thoughts it did on the last token is to put something different in the chain of thought. Like, I thought about that, I should go here, I should go there, that didn't work, whatever, right? It has to use this as some kind of communication mechanism. But it's communicating to itself. It's not really communicating to us. So maybe the words that it's writing don't have the meanings that we would typically assign to them. Maybe there are encoded messages in there. Maybe it's skipping a bunch of steps because it can handle that in one forward pass. It knows that, there's a bunch of stuff in the middle that I don't really have to say. But as a human reader, that would be necessary to convince us of what's happening. Hence the question, is the chain of thought faithful? Meaning, is what's written faithfully representing what the model actually does internally? In general, the answer is mostly. The chain of thought seems to be pretty honest, pretty truthful, pretty complete, especially for smaller models. And this is where it gets dangerous because it lulls you into a false sense of security. But the larger a model is, the more steps it can go through in each forward pass, and the more likely it will treat the chain of thought loosely, like optional. There are many documented examples of unfaithful chains of thought. The most common example is post hoc reasoning, an explanation given after the fact. If the model is biased or using information that it doesn't want to tell you about, for example, gender or racial bias, it will leave that out of the chain of thought. And you can detect this by swapping the gender of the inputs, and yet the model never mentions it. Sometimes the model will make some small mistakes earlier in the chain of thought, and then it will just silently correct that on future passes without bothering to write out, oh, by the way, I changed the 3 to a 5. Actually, just like in the filler token examples in the last section, if you manipulate or corrupt the chain of thought, the model will often still come to the right answer with roughly the same probability. So it doesn't always rely on the chain of thought content, but it just needs the extra computation, the extra width. So we effectively turn our chain of thought into something that's supposed to increase the depth into something that's actually increasing the width. The fact that chains of thought are not very faithful is bad news for interpretability and AI safety in general. People are building medical systems that justify finding things in scans through a chain of thought. It's kind of terrifying. Right now, chains of thought are roughly readable and somewhat faithful. But as models get larger and larger, the chain of thought will continue to diverge from the actual internal reasoning. There is also a research direction that AI 2027 calls Neuralese. This is basically the idea that the communication from one forward pass to the next could stop using English as the intermediate language and switch to the full internal vector representation that models use. After all, there are only so many English words, especially if you're trying to make the sentences make sense. If models could directly output their internal vectors and have that picked up by the next iteration, that would be far more efficient. It would also be terrible for interpretability because we would have no idea what the models were thinking. So far, Meta and others have created prototypes of this, but it hasn't caught on yet, mostly for efficiency reasons. It makes subsequent forward passes depend on the previous forward passes, which means it's very hard to parallelize and accelerate inference for example. But it's possible that AI research will go into this direction in the future, as predicted by AI 2027. If you haven't heard of it, by the way, definitely check out AI 2027. It's a prediction by some expert forecasters about what the future of AI development will look like. And it's called 2027 because all the interesting stuff happens in the year 2027 in that scenario. Finally, in conclusion, we talked a lot about the width and depth of neural networks and how both of those could be a limiting factor in the model's ability to solve problems. The breadth of a neural network can effectively be increased by having more input tokens, which equals more variables and more thoughts happening in parallel, although it is still limited by the attention at each layer. There are techniques such as padding the input with pause tokens to, give it more variables to work with, or effectively letting the model output lots of filler tokens before it outputs its real answer that would effectively increase the width available to a particular forward pass. More width equals more parallel thoughts at the same time. When it comes to depth, that's effectively how long is the model thinking about a particular topic, or how many steps can it do in series. And if you want to increase the depth, you can basically just ask the model to produce a chain of thought so that the same model is invoked over and over again, but with a slightly different internal thought, context, whatever, that is appended to the input each time. That can allow one forward pass of the model to think about substep 1, while a different forward pass thinks about substep 4, for example. Unfortunately, chains of thought are not really very faithful to how a model is actually thinking. The chain of thought and the internal matrix multiplications don't really have a lot in common. At the same time, this could be the moment where we have the best visibility that we will ever have into how models are actually thinking, because the chains of thought are at least nominally in English. But as models get larger and larger, they seem to pay less attention to being precise in their chain of thought because they can just think so much more in each forward pass. If you want to read more about this, I have lots of links in the description below. The first one is about why chains of thought are not explainable or interpretable, and the last one is about AI 2027, so maybe you can check out one of those. And if you liked this video, check out this previous one I made where I answer the question, could transformers bring us all the way to AGI? Please like and subscribe, follow me on X or Substack, or join my Discord. Well, that's all I have for today. Thank you very much for watching. Bye.